So what is the reason to visit an exhibition? Beside exchange and new technologies, you want to see or even better experience new user cases. The VDMA, as partner organization of Formnext, presents innovative application examples with its Additive Manufacturing Working Group in the VDMA user case area. Although we have switched to an online format this year, we do not want to miss the presentation of this important and exciting topic. So the working group decided to go virtual without hesitation. Actually, only almost virtually, because in my studio I welcome Dr. Ulrich Janke, Managing Director at Additive Marketing. Hello, Uli. And Dr. Thomas Reiher, Director Generative Design at Seam Effect Engineering. Good to have you here, both. How are you today?
I'm fine. Hi.
Yeah?
Very
Uli,
good.
everything okay?
Thank you to be here as your guest.
Great to have you here in real person. So working group naturally has more participants, of course, which is why I would like to welcome even more virtually connected participants. So we have Sonja Rasch, Sales Director Manufacturing from Materialize. Hello, Sonja. We have Thomas Papke, Research Assistant at the FAU Erlangen-Nürnberg. Hi, Thomas. We have Martin Grau, Project Manager at Ohnhäuser. We have Carsten Merklein, who's the head of this working group within the VDMA, and he's working at Schaeffler Technologies. And we have, of course, Reiher Gebhardt, Project Manager at the working group Additive Manufacturing. Good to have you all here on board. Hello, everybody. I hope I didn't forget somebody. So this is by far the largest group we present to you, dear viewers, but that's exactly how it has to be, because the projects of the working group bring together the most diverse technology and approaches. As far as I understood from the pre-conversations we had, the project dealt with gripper systems in packaging machinery, and I'm very excited to see what the team has brought with them. I'll hand over to Carsten. Carsten, will you introduce us to the topic?
I hope so. Thank you for the warm introduction. In my function as a board member of the VDMA Additive Manufacturing Working Group, I would like to welcome you all very warmly to this year's Formnext Connect, and especially to the virtual user case area. As you already mentioned, we didn't hesitate to go virtual. I will spare myself the time to talk about the changed boundary conditions or the new normality, but I think the corona pandemic shows us opportunities for new approaches and technologies and makes things possible that would have previously been torn between ideology and dogma. A great opportunity for additive manufacturing? I certainly do think so. With its unique combination of user knowledge, startup enthusiasm, small and medium-sized companies, and entrepreneurial enterprise, the Additive Manufacturing Working Group enjoys a very good reputation within the community. In our presentations at Formnext, we show year after year innovative applications of additive manufacturing at our members, which we were met with great interest by the visitors and which have always led to very good discussions at our booth. So it was also a booth talk last year, during which the idea was born to form exactly these outstanding feature, namely know-how and experience along the entire AM process chain, into a demonstrator. Many companies followed the call and contributed to the success, just as we intended. We assigned the exciting task of realizing the demonstrator together with the companies of the VDMA to a university, namely the Friedrich Alexander University Erlangen-Nürnberg, and thus placed the topic in, as I think, good hands. Another aspect that distinguishes the Additive Manufacturing Working Group of the VDMA in its bridge between science and research and industrial application. This is also expressed, and just allow me the formulation, our Fridays for Technological Future with our lecture series Neues aus der AM-Szene, News from the AM Scene, to which we cordially invite you, true to our motto, AM for Industry. Also on behalf of my colleagues of the board, actually I'm not the president of the board, I'm just a board member, I would like to thank all the member companies of the Additive Manufacturing Working Group and all other participants who contributed to the success of the demonstrator. So come along with us on this exciting journey. With that, I hand over to you, Mr. Gebhardt.
Thanks a lot, Carsten Merklein. Thanks a lot for this introduction. And thanks a lot for the work of our board members. We have 11 in this group. That means we have 11 representatives of different industrial branches and different user and technology suppliers for additive manufacturing. And these 11 board members, they represent also the interest of all our 160 members in this working group Additive Manufacturing. I'm very thankful for those who are today with us here in the studio and online. That's great. And it shows a little bit what's possible. It's really working together on a platform of experts. We have all the same aim, make additive manufacturing ready for industry. That's what we want to get. And it's very important to work together. What I learned in the last 4 or 5 years with all these experts, this exchange of knowledge, that's really the key for success. For example, to know the different technologies, to have an overview of the different technologies and the whole process chain of additive manufacturing. That's a very important point. And the experts bring together their knowledge. So we work also on a roadmap for automatization, because industrial production means automatization. And we have a very interesting and exciting group of about 40 members, people of 40 companies who work on this subject, automatization. Everybody who hears it and is interested, please have a look on our homepage. Please take part. You can join our meetings. We are very happy to get more and more knowledge of experts. That's also a reason why we work on points like communication standard, OPC-UA, which is very important. Traditional machinery also works with these standards, and AM has to adapt to these production systems. That's why we come together with these points. Another important aspect for additive manufacturing, quality and standards. This group of experts have many different aspects which are important concerning quality and standards and safety. Yeah, and so we are surely on Formnext, and I'm very happy to be on Formnext Connect, only online. That's not the best way, but a possibility, and a very interesting possibility, because we get very fast in touch with different people. And this exchange of interests on one side of those who want to use AM, and on the other hand, those who offer technology, this exchange is one of the most important points on our platform. And then in the VDMA, we have behind so many companies, mechanical engineering companies. One of them is Gebhardt, the one Carsten Merklein mentioned. They are a producer of packaging machines worldwide, a very successful company, and high performance machines. So it's clearly that they are interested in additive manufacturing, and they have an existing business model, but they are also opened, and they opened their doors to work on this and to find further possibilities. So we started this project, and it's great to see what the different partners put into this project. First, we have the possibility to have a look in one of these packaging machines, and Markus Schindler, expert from Gebhardt, will introduce the machine. So we have this video, and perhaps we can start it now just to hear some details about packaging machine.
My name is Markus Schindler. I'm responsible and head of for the materials management here at Gebhardt. Schubert designs and builds packaging machines for the food industry, dairy industry, the pharma industry, and so on. So a lot of products from the supermarket get packed by a Schubert machine. The flexibility of our machines come through our tools. We set up tools on our robots, and the tools are as flexible as the product itself. For example, if you have a machine that's packaging chocolate bunnies on one side of a year, and then on the other half of the year, chocolate Santa Clauses, and you only have to replace the tool. Originally, we started delivering the parts as a conventional part. We manufactured them here, we post-processed them, and then we packed them and shipped them to our customers. And the problem was that sometimes the whole process was longer than in a conventional process. We had to think about how we can send files instead of the whole material to our customer. The customer should not slice anything or should do anything in a software, just click and print. Now our customer gets a 3D printer with his machine, and we connect the 3D printer with our digital warehouse. We slice the part with Cura and adjust all the parameters. We print the part out, we test it, and we save the parameters of the tested parts. And this certified printing job we upload on our digital warehouse. A digital warehouse is a storage of all virtual parts and all virtual certified printing jobs he has. Our customer is able to search for parts, he is able to store the parts digital, to print parts on demand from the digital warehouse direct to the connected printer. And the security is the most important thing. That's why we have an IoT gate direct at the printer. Second step is you can encode your certified printing jobs direct to the printer. When the customer wants a new format part for a new packed product, for example, he sends us a 3D model of the packed product, and from the 3D model we can design the new parts. After that we create the certified printing job, upload the certified printing job in his digital warehouse. After that he is able to produce it on demand. It's our task and our solution to help him that he is able to click and print.
Thank you, Mr. Schindler, for this nice overview of what happens at Gerhard Schubert company. I think the approach presented shows that additive manufacturing offers a great potential for packaging machines and also for the machinery customer. In addition to the video, I want to cite Konrad Zanzinger, the CTO of Schubert Additive Solutions, who said, "The company Gerhard Schubert realizes machines for a high variety of packaging tasks by using robots which they develop by themselves. And the aim is a short cycle time for placing products accurately with high demands on dynamics and flexibility. Therefore, gripper systems should have a low weight, which is important when designing tools for robots. And the requirement of low weight leads to the design optimization of a gripper system, which demonstrates the possibilities of AM in context of a packaging machine. The approach of optimization will be shown in the slides. On the left side, the initial design is shown. The component is connected to a robot where the function is to center and hold a packaging shell. And in order to reduce the overall weight of the component, a redesign for the body and the shuffle is conducted. For manufacturing the redesigned version, fuse deposition modeling is used, which is shown for in the video. And the workflow for redesign consists of two main stages. The first stage is the optimization, which is a common approach to optimize a design. And it starts with the analysis of loads, which means we have different load cases, which come to, in this case, the shuffle. And on the next step, these loads and the initial design is implemented in a FE analysis. And with this, we are able to show the stresses and the stress distribution and identify critical part areas. Based on that, a topology optimization is conducted where we use a commercially available software. And this stage is a common approach, as I said, and the more important step is the redesign. And it can be seen that based on the loads, a reduction of the material volume is possible. Since in this case, the optimization is only an orientation for how the component can look like, the next step starts with the real redesign. In this case, functional surfaces are considered and also the result of the topology optimization. For the new design, an identification of critical part areas is done, again by using an FE analysis, and at the areas of high stresses, a failure of the component can happen. The most important step is the redesign and the evaluation of the real AM part, which is the shift from virtual to reality. And in this context, the geometry is measured to prove how close the as-built component meets the target geometry. And the final step is the load test of the component. And the results of the evaluation are shown here. And as we see, in the critical part areas, the failure takes place, and it was expected from the simulation. And this is a very important result, since it indicates process stability and also validates the simulation. In general, a safety factor of 4 was reached, and the total weight was severely reduced. And this was only one possible approach of how additive manufacturing can be used to exploit the potentials. Fuse deposition modeling is a comparatively simple technology which was used here. And further manufacturing technologies also for metals as aluminium or titanium exist, and also other approaches regarding traceability and design exist, which will be shown subsequently in the following. But more details on further opportunities of added value will be given by the participants online and on the stage.
Yeah, I think it's my role right now to explain what we have done. Uli, do you have the clicker?
The clicker, of course.
Yeah, thank you. So I think I just wanted to say 1 or 2 words before. So we have seen very good work on an optimization of the body and the shovel itself. We have done nearly the same work, but we have done a very different approach. So we have tried to do it in a much more automated way. We have used a term called generative design, what is something very close to topology optimization, but a little bit different. And yes, we have prepared a video showing the overall process, showing different software systems, and how we can go to the same goal with a different design as well in a more automated way. So I think I can start it, or will it be started? We do see in the very beginning right here, we have taken a first design of the part, have loaded it into our software and generated design and non-design areas. What means in this point, we are defining those areas, the attachment points, the interface areas, which are not allowed to be changed. Furthermore, now we have added additional material, the called design space, where is material allowed. As well, on these faces, then we apply some boundary conditions. This means fixation, so especially the robot where it is mounted, as well as some loads. In the next step, we can define the optimization parameters. This means, do we want to have a part which is really the maximum lightweight part, or do we want to have a high complex or medium complex part or whatever, and can start the optimization. And now you can see that from the big block of material, step by step, a lightweight geometry is generated, and especially in the end, the real details are generated. You can see over here, everything is light blue. This means everything has a very equal stress distribution, and it's perfect for its use. The step of the redesign as well, you can see over here, it's a 2-click option. It's highly automated. We can generate out of the results of the optimization directly CAD geometries based on NURBS, so that you can have it, as you can see over here, in a CAD geometry with some clear defined interface areas as for some bolts or whatever. With this design, we can go into a verification. So we have gone through this optimization, but now we want to make sure that really our system is able to withstand the loads and we do not have too high or too low distortions. We have gone through this with MSc Nastran, a widely known FEM solver, and you can see how the different load cases, how the part behaves, especially in the torsion moments, and how it withstands everything. The next step, of course, is the manufacturing of it. We have simulated this as well. Over here, we do see the P812 laser sintering powder bed plastics process. We have simulated this with Digimet AM, and you see the part is placed in the chamber, and then you can see the part is built digitally. The coloring is a deviation during the build process, and you see, well, it's a little bit small, but it's 4 millimeters in the maximum. So this cannot be printed in that way. We need some adjustments for it. Furthermore, we have tried to do it for aluminum. So we see the third process. You have seen in a very short animation that we have gone through a re-optimization of the part. Now, instead of plastics, now it's aluminum. And you see how another design was made very easily with just a few clicks. This is the subsequent manufacturing simulation, now for metals powder bed with semi-effect additive. And you see again, we position the part in the chamber and go through the simulation of the process. You see, now we do have two different parts. So we have cut it in half. Why, you will see later on. This is now the simulation of the build process. And again, you see in coloring the deviations. And honestly, again, we see, especially in the foreground, it was again a little bit too high distortion. So we had to take care of that. This is the final part. We have it here on stage as well. And now there's the question, why did we do this part in two different things? And you have seen that this process simulation showed that we cannot directly print it in that way. So we need to take a little bit more effort in the process, in the manufacturing preparation. And this was done by Mr. Schmid from Trovus Tech, and he will explain this process to us from now on.
Hi, my name is Sebastian Schmidt and I'm a developing engineer at Trovus Tech. We were responsible for printing the aluminum part, and I will show you now our whole process from the start to the end. And yeah, let's get started. So here is our component. We use the slicing program Materialize Magics. Unfortunately, it does not fit into the build area with the original dimensions. Not even if we rotate it diagonally. So we have to cut it in the middle and it fits on the building plate. With consultation on the design team, we were able to divide the part and make it ready to print. We can also make perfect use of the dual laser system of our M2 from Concept Laser. The overall Z height was minimized, the construction time was decreased, and time and costs were saved. Compared to the SLS process, our metal melting process requires support structure, not because of the gravity as in FDM, but because of heat dissipation. First of all, the support structure is generated automatically. The support, which have double contact with the component, are moved aside to increase the surface quality and minimize the reworking. The finished data is sliced and loaded onto the machine. The building board is prepared. The machine is set up and the powder is filled. The process starts. After the process, the building board is unpacked and the powder is removed. The components are cut down, finished, supported, sanded and blasted. Our aluminium part is finished. I hope I could give you an insight in our production. As you see, it's very important to have a good interaction between production team and the design team to save a lot of time and money. But you can't just print it out of aluminium, also probably out of titanium. This is something our next team will show you. I'm very excited about it, so have fun, stay safe and goodbye.
Yeah, thanks a lot for this introduction. We are dealing now with titanium, and we have prepared a very old school presentation. Here it starts right now. We took the focus on the gripper shovel that was initially designed in polyamide with the specific weight here of 63 grams. And we have been 3 partners doing this case study together with the guys from Advanced Mechanical Engineering who are doing the design study and the topological optimization, and the guys from Ohnhäuser who are doing the production in TI64 as a certified company according to ISO 9100. And I represent the additive marking team who is doing the paperless process and lifecycle documentation here. The overall goals were, of course, reduce the weight while maintaining performance in terms of strength and stiffness, and while ensuring the operational safety. And yeah, as I said, the paperless documentation and tracking is one topic here as well. We will show some further benefits that we can achieve with direct manufacturing. First, we started very similar to the other guys. We had to understand the functionality and the requirements. Had to, in this stage, very deep understanding of the loads, design space and non-design space. As I learned from the guys from AME, that the depiction of the reality in a numeric model is very crucial to achieve the operational safety afterwards. And because I think all of you can imagine and hopefully agree, operational safety can only be achieved if we have very valid assumptions and not are going, for example, to start the simulation with assumption of material properties that are not really valid. What we see on the right side is the initial part with the load case 1, a bending load case here. And at the bottom, the displacement, so the simulation for this load case 1. And the guys from AME did the same for the load case 2 and 3. And came up here with the initial redesign of the part that you see on the right, where we see the magnitude is here roughly factor 100 times smaller than in the original part. In the next step, we did not only go on the weight reduction here, but take also into account the design guidelines for additive manufacturing, and took into account the challenges as well as the restrictions. So, for example, minimum wall thickness, support structures that have to be generated afterwards to prepare the part for production. The final design achieved a weight reduction of 30% here, although we changed the material to TI64. Due to this material change, we had an increase in load capacity by factor 10 to 15 roughly. And we had a very good support adjusted design. We will see on the next slide, presented by Martin Grau. And we took also into account what you see on the video here at the bottom, that the part has a specific area where we can bring a marking to enable the paperless production and paperless documentation over the whole life cycle. And now I would like to hand over to Martin Grau, who will talk about the production and the support generation.
Thank you, Mr. Janke, for the transition. Due to the optimized geometry, only a few support is required for printing this part. The data preparation defines types and positions of the supports. The tasks of the supports have already been explained. Before transferring the build job to the machine, the exposure strategy has to be defined. The machine also has to be set up for a build job. The main tasks are to screw up a new build platform and fill in the titanium powder. After the process conditions have been reached, metal powder is welded layer by layer into parts. After printing and depowdering, the build platform is removed. The extracted powder can be reused after a refreshing process. As a result, very little waste is generated during the build process. Before the printed build platform continues the process chain, the parts are checked for the printing defects. The high process temperatures result in high residual stresses in the parts. These must be removed in an annealing process to ensure the dimensional accuracy of the parts. After annealing, the parts are separated from the build platform by a bandsaw and assigned to their individual orders. In this step, the test samples are removed and tested. After this test has been successful, the remaining parts will be approved to further processing. The printed marking ensures that the parts are assigned to the correct orders. This avoids confusions. As each part has supports, they have to be removed by hand and the leftovers have to be ground for a clean surface. Different processes are applied to refine the surfaces depending on the application. These are typically blasting, vibratory grinding, and electropolishing. Depending on its requirements for the part, these processes can also be combined. For higher accuracy, as well as for threads and fits, a CNC machining is used. This is usually a milling or drilling process. The quality assurance department checks compliance with the acceptance criteria specified by the customer before a part is delivered. After successful inspection and subsequent documentation, the parts are shipped to the customer. The documentation is currently done in paper form. The data matrix introduced into the CAD model makes it possible to do the complete documentation digitally. And that will be shown by Mr. Janke again.
Yeah, thanks a lot, Martin. So, as we can see here, our main topic here from additive marking is the traceability and documentation in the global and distributed production, as we've learned in the initial video about the gripper system. The main idea is to come up with an on-site and on-demand production. And so our topic here is to bring in machine-readable codes in the parts, so that you can document the whole process steps over the whole process chain just digitally. So the part can be scanned at each process station, for example, and you can generate your own digital twin for each individual part. And so you have, according to the, for example, ISO 9001 certification and 9100, as we've heard from Ohnhäuser, a very good and safe documentation over the whole process step, so that you can be very sure afterwards that the part has been printed on a qualified machine with qualified material by qualified personnel staff. And this totally without paper. And as you can see on the small smartphone, the parts are directly scannable when they're removed directly out of the powder bed. So the marking is able to be scanned out of the powder bed, after blasting, after heat treatment, and over the whole process chain. And this is where I come to the end. Here we have some contact details for further questions and cooperations, of course. And then I would like to hand over to Sonja Rush, who will talk about serial production, I think.
Yes, thank you, Dr. Janke, for the kind transition. And yeah, thank you, Dr. Gebhardt, for having me here on the panel. Yeah, we at Materialize, I don't know if you add my presentation or not. I'm not sure.
Yes, should be.
Okay, okay, yeah. Thank you. Yeah, we at Materialize here see every day in our business that many companies are really fully enthusiastic and also very convinced about AM as such, but yeah, many of them just try to replace conventional technologies, and then they are disappointed and frustrated and hardly find any profitable case. And I always say, if you do it, then do it right. And to bring it to a success and to really find profitable cases, yeah, there are 7 key factors to consider. So first of all, many companies tend to invest quite too early in their own hardware and software. And yeah, then they struggle, and even worse, the decision later turn out to be expensively wrong. So I always say, before every make or buy decision, yeah, it's really essential to gain first experience and to identify suitable applications and business cases. So first the case and then the investment. And I know also, yeah, good cases are really difficult to find. So if you don't know which are the right parts for AM, yeah, look for the most cost-intensive parts with low amounts and special paints. So parts with high stock cost and high recovery cost, parts with a lot of assembly or welding, or parts with low performance or low reliability. And when you finally have identified already promising parts, then there comes the most important rule. Do not substitute, or you will hardly find any good case. So when you see the example on the left side of the gripper, a gripper printed like this would be minimum 5 times more expensive than milling. And even if you put lightweight structure on it, which is the typical task when customers come to us and say, yeah, please make it a little bit lighter. But yeah, you are disappointed then, and you will not do it because yeah, it's 5 times higher. So just with an AM design, you can, like the one on the right side, then you can get close to the milling price, or even in this case, cheaper than milling. So really very important, do not substitute and have the drivers for AM in mind. I don't want to tell them all, so because they are all normally well known. So think additive, design additive, combine 5 parts, 5 parts to 1, add functionality and so on. Or just simply reduce build times by reducing material or support structure and so on. So I guess these rules are all well known. And when we look at the redesigned gripper on the right side, yeah, it's now not only much cheaper, but it's also 95% lighter, which means you can go easily 2 robot class down, which saves you a lot of money. And you can run much faster cycle times. And due to the adjustments of the suction channels, which you can't see here, you also reach much better performance and much better reliability. But, or let's say that brings me also to the next important rule. If you first design conventionally and then do the redesign, then you have double cost. So save money when using additive design consequently from the beginning. Yeah, and the gripper example also shows you should not just look only at the direct part cost. If you have identified suitable parts and then send them to your purchasing department and ask them to compare the part cost, I can really guarantee you, you will hardly find any case. The AM cost will always be much higher and you will be disappointed in the end. Purchasing can really kill the business case. And as long as the design is not an AM design, costs are always much higher. And that's especially the case for metal. In plastic, you find some cases, but in metal, definitely not. And I do not want to recommend to surpass your purchasing department, but please involve them very early and talk to your supplier or your own production already very early in the development stage to discuss the opportunities and also the cost-saving potential. Yeah, and then finally, you should always look at the full TCOs. Do not forget that with conventional methods, you always have additional costs. And these additional costs are sometimes even higher than the initial part cost. So you should consider this in your comparison. So include all your additional costs like weight saving costs, savings for additional design changes, less inventory, reduced logistics, reduced assembly cost, better performance, higher reliability, and all these things. Yeah, and then you will explore the real business cases. So let me summarize here. First the case and then the investment. No substitution. A consequent AM design from the beginning. No pure part cost comparison and the full TCO consideration. That are the key factors for success. Yeah, and of course also for cost savings. Next page, please. If you then finally found a good application and you are fully convinced by AM as the best manufacturing technology for your own serial production, do not forget to consider enough time to establish and to implement the proper serial AM process. Because also with AM, you want to have a repeatable, a reliable, and a traceable production process, as also Dr. Janke said before. And that is similar to conventional technologies, always very time-consuming. So you need to follow a full NPI process, and you need to plan enough time for this. So it's absolutely important that you specify at the beginning all important requirements. So not only the tolerances, but also mechanical properties, surface finish, yeah, maybe assembly conditions, lifetime requirements, and so on. And then you check the feasibility for this, and not only for one lucky shot, you also need to test it for many more under different conditions and in different areas of the machine, and maybe also on different machines, so that finally there are no surprises when you really scale up your serial process. Yeah, and as we said before, also it's really important to have good process engineering. You also need to have or implement in-process monitoring. And you need a complete overview and management of your full production process. So you need to know when, on which machine, with which parameters did you build the parts, was also mentioned before. So you need to track all pre- and post-processings, and of course, all the related powder batches, the tensile bars, the other test bars, parts, and so on. So, and similar to Dr. Janke before, for the full traceability of all process steps, you need a unique part identification. So a distinctive labeling. And then of course, the right software in place to trace all this. And in our own production, we trace and control everything with our Streamix software. Finally, of course, you need a proper quality management system in place. To have the complete package ready. So as you see, finding the right applications and doing certified manufacturing is a very complex topic. And yeah, of course, you can try everything to explore and set up everything on your own. But we can also offer you to go this way together with you as a neutral and experienced partner with our full Mindware consulting service behind it for each individual step and depending on where you are in your production process. So we really like to invite you to take the shortcut with our Mindware consulting team. And yeah, thanks again for having me here on the panel.
Thank you so much, Sonja. Thank you, all of you. My question, what is the conclusion? What are the key findings you took out of it? Probably, Thomas, starting with you. I mean, you worked in that group. How was the cooperation inside the group? And how did you summarize the results? And what was the conclusion out of the project?
So beginning from the end, summarizing the results you've seen today. So it was quite complex to get all these people together, but yeah, everybody was working hard on this, especially in the last weeks. Nobody knows who can be here or not. Yes, so it was quite good to work together because we have had yeah, more or less two different parts in this packaging machine. We had a lot of requirements for the process, for the optimization, for the design, etc. So a lot of things we had to talk about. We had to see how fits it together. And especially as we have seen from our side, from the design with the generative design together with Trovus, I think it was the same for the others as well, where we had to really not just design something, but talk to those who are producing it and really make sure that we are thinking additive from the beginning, as we've just heard, but then make sure that it fits together. Okay. And this is important, and I think the overall finding would be additive manufacturing can be a big benefit for those parts, but we really have to talk to each other and make sure that all of the steps are covered and perfectly work with each other.
Great. Question to probably Thomas Papke. So is that being implemented? What has been implemented of this solution you work together on?
What we can implement is the design, because we tested it. We showed that it's enough. It shows enough strengths, and the loads are low enough for the design. And even for a plastic version, we have a safety factor of 4, which is very good. But also the other materials also showed the potential and also different approaches of optimization.
One question to you, sorry, Thomas, again, because I've seen you went through that simulation and it was purely done as software, right?
Yes.
There was no test part printed and put under a stress test. Thomas, you did a stress test, right, with a part, right? A real stress test.
We did a part testing where we also selected the boundary conditions, how the part is clamped in the machine. And of course, we had different load cases, and we tested the most critical case, and we showed that the part can withstand the loads.
Yeah, this is, sorry, but this is the point where we had a little bit less work, because we took this outcome, we know about the loading conditions. We could take those information and put them into the software, and then we were fully trusting our software. Well, but we knew that there had been these tests.
Okay, you had the preconditioned data available. Okay,
that makes it much easier.
So, wrapping this all together, wrapping up again. Are there findings from each other that you could take with you? I mean, this is basically one of the targets, right, of such a user group, that afterwards you say, hey, what Thomas did, that was cool, I can implement this in my processes. Had this happened, or would you say today, what the others did, I could do better? Uli?
So I would say it has to go hand in hand from the very first idea and the definition of the main goals that we want to achieve with the optimization. And talking about our specific task to bring in an individual part marking, it's very important that it's already considered in the design phase and in the optimization phase. I think it doesn't matter if it's done manually or in the software tool, would be fit also very, very good together.
Okay, so there are two questions from the audience I need to address here, and they're both to Uli. The first question is from Dr. Heinrich Jürgens. How do you get around the contrast issue when marking parts in the same color? I mean, it's all the same color, right? That is a problem for machine readability, I suppose.
Yes, it is, but we solved it. So if we have a very detailed look on the part, you see that we don't have a 2D engravement or embossing, but it's a very specific geometry that we use for each single module of such a data metrics code, where we are going to achieve a contrast by light, more or less, so that we are able to scan the part with the usual smartphone. So iOS, Android, doesn't matter. And so you're able to scan the part.
Then there's the next question from Patrick Stein. I hope it's correctly addressed to you. But did you consider green application such as the circular economy for your software?
Yes, of course. So I think we've learned it from some panels yesterday that circular economy is a very good driver of additive manufacturing, and we're able to reduce weight and material. And for example, due to the markings, we're able to start the recycling for stainless steel and for tool steel or for aluminum, so that you're going to improve the recycling process.
Okay, cool. So we have different companies. Trovus, by the way, hello Sebastian. I thought you will join us now. Good to have you on the panel. Thank you.
Hi, nice to be here. Thanks.
Thank you for being here. So Trovus produced one part, and then we had who produced the other part?
Ohnhäuser.
Ohnhäuser. Are there competitors in a certain way or not?
No, I don't think so, because we mainly focusing on aluminium production, and I guess our colleagues here have more focus on other materials, for example, like titanium. And I guess it's for little companies like us, it's more important to focus on one thing and do it right, instead of every material is so handling differently, even in the metal process. So it's not easy to handle every metal in a different way. So I guess it's a good way to focus on one thing, and every company has its own way to do it.
But Martin, that would lead to a question to you, though. What is the motivation to participate in such a user case for you and your company?
We want to show our processes, because many of the parts we produce, they are under you can't talk about them because they are secrets, and with these parts we can show for the visitors, and they can learn how good we work.
So it's about to present the capabilities of your solutions to the world. Okay, Herr Gebhardt, what is your conclusion after all this project? What would you say? Did you enjoy it, working together with the others, or?
Final statement, yes, great, perfect. That's what I want, what I like very much. Working together, these people, you see experts from university, from company, sales, technical departments, and they are working together, just looking for best solutions. And learning how every expert has a knowledge and a solution, bringing it together. I think this is the key for success of additive manufacturing, and we have to do it. That's the future of additive manufacturing. It's really amazing in this group also to see young people, dynamic and new ideas, just how they work together, and normally open mind, not in the way, you're a competitor, I don't speak with you. That's really great. I like it very much.
Great. Thomas, if it comes to the company Schubert, I mean, in the end, that was a combination out of different disciplines, but Schubert was kind of the end customer, right? So what was the feedback from them, to you and to your work?
We met them one day together with Mr. Gebhardt and showed the results of the work, and they also built all the other components around the body and the shuffle. And I I think they were impressed how much the design can be reduced to the fundamental surfaces, for example, and how much weight can be saved by a new design approach.
So is there like a follow-up project together with Schubert, or is it this is it now for the user case, Thomas?
I think for the user case, it's it. So for this part, more things will come together with them. I think they have seen, they have shown how far they are with additive manufacturing. And now this user case was a lot about the question of design, of how to get to these designs. They do have these hundreds and thousands of different products they are packaging, and all of them have different grippers, etc. And they need a good way, a good design methodology to get to a perfect part very fast and reliable. And I think other things will come.
Okay. Sonja, quick question to you. I mean, following your principle, Schubert must have found one solution or one application, right?
Yeah. They are very far. That is really, you can see how far they are. They're even farther than many others. So, that's really impressive.
Okay, great. Okay, thanks to you all. I mean, I think that was an exciting user case. It nearly felt like we had been in a real Formnext, at least with the two of you, but with your insights, thank you so much. Great work, great achievement. Good luck for the following user cases in your working group. I'm keen to see the next results and hope you keep me posted. Thanks to the audience for the interesting question, and we keep on going with our program. Thanks a lot to all of you. Good luck. Bye-bye.
Thank you.
Thanks.
Thank you.